Now, when we discharge a capacitor, if you go back to this circuit here, so this was charging. Now, once the capacitor is fully charged, you're going to take this switch and connect it to this point. So the switch goes from this point to this point. So do you see that the capacitor is not seeing the power supply when you discharge a capacitor? So what happens is that when the capacitor is 100% charged and you remove the body, it's not seeing that body anymore. So it cannot get any energy from the body. It's just going to lose the energy. So this is called discharge. So now the capacitor is acting as if it's almost like a body. And that's the use of the capacitor. So you can use the capacitor to store energy. So this is almost acting as a body. And this body is just going to supply the energy to the resistor. Now, a resistor, what a resistor does is that it's just to, so it's just called loss. So you just kind of, so it's just a loss of energy. And this loss of energy, again, I think if you remember from the last class, we said this is called the Joule heat. And there is a way to calculate that. So the Joule heat is I squared times R. So it's called I squared. So for example, it's the current that is going through the resistor. You square it, and then you multiply it by the value of the resistance. It tells you the Joule heat. So the Joule heat is always going to be given as something that is in a unit called the watts. It's a power, because it tells you the so how much amount of energy is being lost in every second, right? So joule per second is called the watt. So now when this switch is connected here, you can see that, again, if you go back and apply the Kirchhoff's rule, in this case, if you go in the, let's say in the counterclockwise direction like that, right? Then there is no power supply, you just get this equation right here. So the negative Q over C is the voltage across the capacitor, and then this is the voltage across the resistor. If you rearrange this equation a little bit, you obtain this equation, and then doing some integral here, you get the charge and the current. Now, again, I want you to understand the difference. So let me write this equation. Let me call this equation number 3, and let's call this equation number 4. So notice how equation number 3 and equation number 4 is different from equation number 1. Call this equation number 1 and call this equation number 2. I'm sorry, call that equation number 1 here and call this equation number 2. So equation number 1 is the charge on the capacitor. Equation number 2 is the current. Remember that this is when you're charging the capacitor, right? So 1 and 2 is when you're charging the capacitor, and then 3 and 4 is when you're discharging the capacitor. So you want to know that difference. So again, so let me write these two down, because these equations, I think those are the only 4 equations that you need to remember from this section. So equation number 3 and 4 is for discharge. So let's write it here, discharge. Again, I apologize for my writing here. So this is for discharge. And then let's write two set of equations for charging. So when you're charging, the charge is going to go as Q of T. So Q of T is going to be C times epsilon, that's Q max, into 1 minus E to the negative T divided by R times C, like that. That's my writing here. So that's how the charge shifts. So when you're charging a capacitor, the charge at any time is given by that equation. And the current, I of t, is given by this equation here, is this over that times e to the negative t divided by r times c. So just those four equations, you can solve all the problems in this section here. Now, just one more concept here. If you guys look at this equation, what do you think this Qi here represents?
Initial charge.
Is the initial charge. Now, Qi, you should see that this Qi is equals to F. Because when the capacitor is discharged, right? When it starts to discharge, it was already at 100% before it starts to discharge, right? So it means that the initial charge on the capacitor is just epsilon times C. So you can take this Qi here and substitute here, for example. So if you take this Qi and you substitute, you can substitute this value here, this value. This is given by that. So that's Qi. So four equations that you're going to use to solve all the problems in this section. Two of the equations is when you're charging the capacitor, and two of the equations is when you're discharging the capacitor. So just know the difference. Each time that you solve a problem, you just ask yourself, am I charging the capacitor? Am I discharging the capacitor? And then you can always substitute all the values. All right, I'll let you guys look at some of these practice quizzes here. Now let's look at this example. I think solving one example can help to really explain some of the things that we've been looking at. So let's look at example number 27.9. And in this example, we're going to charge a capacitor in an RC circuit. So the very first thing is that I want to read this problem and make sure that we understand all the quantities that are given here. So it tells me what the charging voltage is 12.0. It tells me that the capacitance is equal to 5.0 microfarads, and the resistance is 8.00 times 10 to the power 5 ohms. Now, when the switch is placed at point A, so when my switch is placed right here, so it means that I'm charging. So now the capacitor is seeing this power supply, so this is the charging. And then for part A is saying that calculate the time constant for the circuit. And then you want to calculate the maximum charge on the capacitor. And then you also want to calculate the maximum current in the capacitor. And then write down some equations for the charge and the current as functions of time. All right. So we're going to calculate 5 quantities here. So the first one, number 1, is to get the time constant. Number 2 is to get the maximum charge on the capacitor. Number 3 is to get the maximum current. Number 4, we're going to calculate the charge and the current on the capacitor, right? So if this was something that you have on an exam, you want to read this problem very well. So remember that it says that this is an uncharged capacitor. It means that at the beginning, so at t equals to 0, the charge on the capacitor there is nothing in there. It's an uncharged capacitor. There is no charge on the capacitor. At t equals to 0, Q is just equals to 0. So looking at this problem, it tells me that this is a problem where I'm charging a capacitor. So I'm charging. So I know what equations to use. So I know how to calculate my time constant, for example. So if you just go in here, again, as I said, each time, make sure that your resistance is in ohms and your capacitance must be in farads. So it means I need to multiply this by 10 to the -6. So if the resistance is in ohms and your capacitance is in farads, then your time is going to be in seconds. And so if you calculate this time constant here, you get about 4.00 seconds. Now, let's calculate the maximum charge. So again, the maximum charge is just given by this equation here. So Q max is equal to the capacitance times the charging electromotive force. Now, if you substitute this value here, now in this case, if you wish, you could leave it as microfarad here. But if you leave this as microfarad and you leave this in volt, then this is going to be in microcoulombs, right? But if you change this to farads, then this will be in coulombs. But you could leave it like that, that should be fine. So this is 60.00 microcoulombs. Now, in the next part, you also want to calculate the maximum amount of current, which is just given by this equation. So it's calculate the maximum current. So the maximum current is just given by this equation. And if you substitute, you get 15.0 microamps. Now you can write this expression here. So Q of t and I of t. Now, I want you guys to look at this equation very carefully here. So let's call this equation number 1 and call this equation number 2. Now, I want to go in this equation and substitute so let's substitute Q equals to T equals to 4.0 seconds. Now, if you put T equals to 4.0 seconds into equation number 1, what do you get? Zero. Is it 0?
You get, yeah.
Because when T equals to 4.0 seconds, exponent of -4.0 over 4.0 becomes exponent of -1, right? So in your calculator, you're going to put 1 minus exponent of -1. And that number should give you something about 0.6 something, 0.62, 0.63. And then you multiply that by 60, right? So again, remember what this time means. So remember what the time constant means. The time constant tells me how much amount of time that the capacitor is going to take to charge up to about 62, 63%. So for example, I want you guys, if someone has a calculator, let's calculate this quantity and see.
It's 37.9.
37.9. Now, what is this number in here? This number in here. So 1 minus e to the -1 is 0. Is it 0.62 or 63?
0.63.
0.63. Now, if you multiply 0.63 by 60, then you get the, is it 37?
37.9.
37.9. And this will be in microcoulombs. Microcoulombs.